Well, okay, so let's start. Yesterday's lecture was still about on technical thing. We need to be able to speak about differentiable function. We need to be able to compute the differential. We need to be able to speak about chain rule and so on. But these are kind of technical things that are required, but are not the heart of our study. So let's go back in business. So now we really want to understand how to attack the study of the geometry of a surface in runner 3. So let me start with another definition, just for convenience. As usual, S will be a regular surface in R3. And now, since we learned what is a differentiable function, it is very convenient to define what is a vector field. So a vector field V on S is a differentiable function, and now we know what it means, V from S to R3. Okay? So basically, to each point of the surface, you associate a vector, but you need to do it in a differentiable way. And now you know what this means. Okay? Now, in fact, just to complete the definition, let me say, because often this will come up. So a vector field V is called normal and unitary if V of P, for any point, for any P in S, V of P is orthogonal to the tangent space. Okay? This is normal, unitary if the norm of V of P is equal to 1 for any P. Okay? So today we are going to start studying the behavior of vector fields and normal vector fields on a surface. Before doing that, since there is always an ambiguity, you will see it. And then, for my experience, this is a source of confusion for students. So let me freeze for a moment this definition and make just a comment. When you have a surface in R3 and you want to write down a vector field along it, what you usually do, and you will see it now in practice, is that around some point, since you know that it's a regular surface, you have the usual chart, the usual picture. Okay, so you have this open set U and the map X. Okay? So usually we will confuse. So now the vector field is really here. Okay? It's on the surface. It's a map which assigns to every point of the surface, in fact, not even inside the local chart. I mean, this local chart. It might be here, here, here. A differentiable map to R3. Okay? We will often make a confusion. You have to be clear about this. It's an irrelevant confusion, but it's a confusion, so we have to emphasize it. The map V, so the vector field on S, with its composition with X inverse. So if you have at every point of the surface some vector field here, V of P, okay, you can also think of it, so this P will come from a point here. Okay? Of course, X is 1 to 1. Okay? So in some sense, you can think of a vector of R3 pointed at this point of U. Okay? And we will make this confusion. You will see it. So you have to be always a bit careful about where is the domain of the vector field. So for example, but this is just a simple example to warn you about something that's going on later. Let's take, this is also an excuse to make a little exercise. So suppose we have a surface which is a graph, for example. For example, the graph, in fact, it's given by 2z is equal x squared plus y squared, okay, in R3. Now, S, in our notation, is the graph of a function f, because you see, for example, just dividing by 2, I have z equal to something, okay? F, if I look at f as a function from R2 to R, taking xy into 1/2 of x squared plus y squared, you immediately see that this is exactly the z to be put here, so S is equal to the graph of this function. Okay? In particular, we have seen in general, so why this is a regular surface? Well, the function is certainly differentiable, it's a polynomial. Okay? And how did we prove it that a graph is a regular surface? Actually, graphs have the special properties of being covered by a single chart. There is one single chart which is good for every point of the surface. Okay? And which is this chart? Is exactly, in some sense, the map F suitably changed. Okay? So x, for every point of the surface, I can think of x. Now, my domain will be the whole of R2, because actually we should take in general the domain of F. Here, F is defined over the whole of R2. So I take R2 here, and I go to R3, taking, remember, our notation is to call the coordinates on R2 U and V, not to be confused with X, Y, and Z, okay? So U and V, and this goes to, in some sense, the graph map. So U, V, 1/2 U squared plus V squared, okay? And now, I mean, we know it in general, so in this particular case, you can double check that this is actually, this verifies all the requirements for something to be a chart, okay? But what I want to underline here. Now, for example, we said the tangent space at a given point, remember, one proposition we proved, as a corollary of one proposition we proved, is that the tangent space at each point is spanned by the vectors dx du, dx dv. So what are these vectors in this case? Well, xu is really the vector given by partial derivatives with respect to u. So it's simple. It's 1, 0, u. Okay? Now, xv is the other one. But now, here is what I wanted to say about this little confusion. So, these vectors are defined where? These vectors are defined on U in the general language, on R2. So give me U and V, and I compute these two vectors. So these are not vectors on the surface in some sense. Okay? These are vectors on the domain of the chart. So now if I take a point P, what are the tangents? So, and when I said something like these two vectors are a canonical basis of the tangent space, what do I really mean? Well, to be extremely precise, I should say, well, take a point P. P will be x of some point on U. So it will be x of U naught, V naught, for some choice of U naught and V naught. So the tangent space at P to S is the span of the vectors xu at U naught, V naught, xv at U naught, V naught. Now, these two things are vectors at the point of the surface. Okay? Because I compute it at the corresponding point. Okay? So U naught, V naught is the value here, but I compute it at x of that. Okay? Okay, think about this. I mean, and you should just think of it, because now this ambiguity will come into the game often. Okay? So sometimes we will be careful and sometimes not, and you have to not to fall into the trap. Okay? So let me erase this and let me go back to now normal vectors. Now, let's still draw a picture. Now, the problem is, how many normal vectors do we have at a given point? Well, we have our surface. Well, in fact, how many unitary normal vectors do we have? We pick a point P on S. We have a tangent space. So the tangents, we are in R3, and this is a plane. So how many unitary normal vectors do we have at P? 2. Okay, I can pick this one or this one. No other choice. There is no other way. Okay? Well, that's clear. Now, the point is, this was at a fixed point. Now let's start moving the point, and let's see what happens. I mean, how many choices we have globally on a surface of unitary normal vectors. Well, let's make an intermediate step. So let's see first what happens, not globally on the surface, but on the piece of the surface which is covered by a chart. Okay? So if X from U to S is a local chart, then there exists at least one. Then there exists at least one unitary normal vector field on the part of the surface which is covered by this chart. Okay? Now, the part of the surface which is covered by a chart is it by itself a regular surface. It's an open piece of a regular surface, so it's a regular surface. Okay? So you know what it means for something to be differentiable on X of U. Okay? How do I prove it? Well, think first to the point to be as fixed. So you fix the point P. How do I construct one of these two in R3? Well, that's simple. If I have a basis of the tangent space, if I have two vectors which span the tangent space, then the third one, I mean, I complete it as an orthonormal, in particular, well, it doesn't really matter if they are orthonormal or not, okay? Any basis, I can complete it to a basis of R3 with a property that this one is orthogonal to these two, okay? So in particular, there is a simple algebraic way to do it. Give me these two vectors and take the vector product of these two, and now, depending on which one is which, it will be either this or this, okay? Up or down, but one of them is I can write it like this. But the point is that on X of U, I certainly have a basis of the tangent space automatically. The one I just erased on the blackboard, okay? So notation, this is just to simplify. So notation, the vectors I wrote before, dx du, dx dv, so in fact, notation would have been better. So this is, I write in short xu for this. Probably I've already done it, but I mean, and this is xv, okay? Partial derivatives, I put it little down on the right, okay? Subscript on the right. So we know that xu, xv is a basis. Is a basis, and here, now, on this lemma, I will be precise about the ambiguity I said before. So it's a basis of what? It's a basis of Tx of P. So now, well, let's call it Q, because usually we call Q the point on the domain and P the point on the surface. I mean, these are names, so you can change it whenever you want. But I mean, so whenever Q is a point on U. Okay. So this is what I tried to convince you before. Okay. So you have to put this, when you compute this at some point UV, you really are taking the basis at the corresponding point X of UV. Okay. Now, so then define a vector n, and let me pull it a superscript x, an x at the point Q of U to be nothing but xu at Q wedge x, so the cross product, the vector product xv Q, Now, for what we said before, this is certainly a normal vector, but I want it unitary, so I divide it by its norm. I know that this vector is non-zero because this is a basis. Okay? So I'm dividing by something which is certainly not zero, and this is a basis. So where is this map going? So Nx, written in this form, is a map from U, takes a point on the domain of the chart, to R3. You see why I'm emphasizing this little ambiguity. So strictly speaking, N is not a vector field on S or X of U, but it's a it's a vector field on U. Okay? So we have to do something if we want to adjust it. Okay? Now, but first, is it a vector field? Meaning, is it a differentiable function? Well, it is, because X is a smooth function. These are partial derivatives. The vector product is certainly a differentiable operation. Dividing by the norm is certainly a differentiable operation as long as the norm inside, the vector inside doesn't go to zero, and we are sure that this will never happen. So this is a differentiable function. Okay? And it has the property that Nx, so this is differentiable. And in some sense solves the problem, besides it has the wrong, forgetting the only problem that it has the wrong domain. In which sense it solves the problem? It is really, it's certainly unitary, because it's a vector divided by its norm. And it's certainly, so Nx at the point Q is orthogonal to the tangent space to X of Q, by definition, for what we construct. Okay? Well, and let me just write it for memory, but an X of Q at every point the norm is equal to 1. Okay, so this looks like a unitary normal, but we have to change the domain. Well, but to change the domain, it's easy. We compose it with a local chart. So then define N N of P to be nothing like but Nx composed. So I take the point P on the surface, I pull it back to the domain of the chart. Okay, I don't draw it, the usual picture. Now, every time you think of a surface, you should think of the usual picture, and this is X inverse of P. Okay? So this is just a way to change the domain. The map, in some sense, it's the same. It's just defined on the two corresponding domains, okay, via the map X or X inverse. So very good. So this ends the story, because now this is, of course, still a differentiable function. It's a composition of two differentiable functions, and at every point it's unitary and normal. Okay, so this proves the lemma. Now, of course, if there is one, so here I just produced one. In fact, in the picture, I don't know, because I never said if this is the first or this is the second. Of course, the order of the two vectors when you take the vector product is what is telling you if you are going up or down. Okay, so since I never said if it's this wedge this or this wedge this, I don't know in the picture. I cannot tell. But I certainly produced one, and now it's defined at every point of the of the chart, covered by the chart. At every point covered by the charts, now I'm supposing it's the one going up, I have this differentiable vector field. Okay? But now, of course, how many other choices I had? Well, only another one. So on X of U, either I take this one or I take minus this one. There is no other possibility, because again, at every point it's a plane in R3, so at every point there are only two possibilities. Okay? Now, and in fact, let's prove it in some sense, but it's a simple topological argument. You see, choosing one of these two is essentially deciding from which side you are looking at the surface. Are you looking from above or from below? Or in other terms, from inside or from outside? Okay? So, another lemma. If S is connected, I mean, you need one simple topological condition. If you have two unitary normal vector fields, so let's say N1 and 2 are unitary normal vector fields, on S, then there are only two possibilities. Either N1 is equal to N2 or N1 is equal to minus N2. Okay, this is the intuitive situation. So it is certainly true at one point. Now the point is it's true on the whole surface. Okay? Well, how do you prove it? This is just topology. Because now, for any P in S, if I evaluate these two vector fields, so N1 at P and 2 at P are two unitary normal vectors at that point. So these equations hold at that point. So either they are the same or they are opposite. There is no choice. Okay? So these are unitary normals. Normals at P. So N1 at P is equal N2 at P, or N1 at P is equal minus N2 at P. Okay? Well, now the problem is, if I change point, so this is true at every point. So what is the only problem? If you understand the problem, you solve it immediately. What is the problem? The problem is, if I take now another point, Q, then it's still true that at Q, N1 of Q is equal N2 of Q, but the problem is, are you falling in the same case at P? I mean, so suppose at P this was true. Now take Q. Maybe this one becomes true. Is it possible or not? What the lemma is saying is not. Okay, the lemma is saying if something like this is true at one point, it's true over the whole connected component of this point. Okay? And how do you prove it? So suppose you have 2 points in the same connected component for which at P this is true and at Q this is true. So now a little intuition, I mean there is something funny. So somewhere you would like to say, if this was, for example, a curve, no, I mean a one dimension, somewhere in between, I mean at some point in between something strange has to happen. Now of course this is a surface, this is not an interval, so you cannot say, well this is a positive function here, negative function here, in between there is a zero. This is what you should have in mind. But of course this is not a one-dimensional problem, and this is not a positive or negative. These are vectors. Okay? But that's simple. How do you argue? S, since these equations are true at every point, so either this or this is true, if I write S is equal A union B, where A is the set of points on S, of course, such that the first one is true. N1 at P is equal N2 at P. And B is the other one. The set of Q, if you want to give it, such that N1 at Q is equal minus N2 at Q. The above simple observation tells you that S is the union of these two. So every point falls either here or here. Now, of course, I'm assuming it's connected. So, of course, the claim is that this is an open decomposition of S. An open, non-empty, I mean, of course, the contradiction, now you argue by contradiction, okay? So suppose that these are, well, okay, how do you argue? What are, topologically, what can you say immediately about A and B? They are closed. They are certainly closed, because these are equations, and continuous equations, in fact, differentiable equations. N is a differentiable vector field, okay? So the set of points where these two objects are the same is closed, and where they are opposite are closed. So these are both closed. So at least one of them has to be empty. Otherwise, you contradict the connectedness. Okay, so A and B are closed. And this implies A or B empty. And that's it. End of story. Okay? Now the problem is, okay, so now what do we know? We know that at every point there is a unitary normal. On the piece of a surface covered by a chart, there is a differentiable choice of a unitary normal. In general, on the whole surface, or that is on the whole connected component, I mean, we usually assume, even without saying that surfaces are connected, but in principle they could be made of pieces, okay? So on a whole connected component, I have only two choices of unitary normal. But now the question is, does there always exist a unitary normal on a surface? So remember, locally, yes, because every surface is x of u. Okay, so on a piece of the surface which is given like x of u for some chart, there is a unitary normal. But who is going to tell me if there is a unitary normal over the whole surface? Well, nobody. And in fact, it may be false. Okay? Wait a moment. Okay, so let me give a definition. So the surface where a unitary normal exists are special. And so let's give them a name. Definition: if a regular surface S such that there exists a unitary normal globally, that's the point, N, defined over the whole of S to R3, is called orientable. Well, the name is right, because you see, if you think of the choice of a norm, of a unitary normal, as to choose the choice of a side where to look to the surface. Okay? Orientable means orientable surfaces, they have a side. Okay? I mean, you cannot explain names. I mean, if you like it, or no, you give it another name. But I mean, it is a meaningful name. So examples. One, well, as I said, I mean, usually you should start. There is in all your everything there should be example 0, the plane. Okay, so the plane is the simplest regular surface of R3. So let's do it. I mean, in fact, I was going to start from example 1, but let's start from example 0, but even without writing anything. Take a plane in R3. Is it orientable? Well, a plane in R3, you can actually take as unitary normal the normal vector to the plane. One normal vector to the plane, one of the two. And this will work at every point. So n, in this case, will be the constant vector. Of course, when I draw it pointed at every point of the plane, but actually as a vector, it's always the same vector. Okay? So the plane, you take the constant vector field given by the norm, one of the two normals, okay? And that's it. So now, in all your list, so example 0 is the plane. Example 1, the sphere, okay? So is the sphere orientable or not? Doesn't really matter now. Let me simplify notations. So let's take S2R, well, S2R. Well, S2R, no, let's do the general case, okay? Center with a given center and a given radius. Is it normal or not? Is it orientable or not? Well, let's draw a picture again. So this is the point P naught, and this has radius, okay? So at a given point, P, we should think of the tangent space at P and try to imagine a normal vector. But we know it. So what are the only two possible choices at P? P minus P naught or P naught minus P, the one you prefer, okay? But then, well, so that means N from S to P naught R into R3. This is the object I need to define, okay? A unitary normal, so a vector field, so differentiable, which at each point it's unitary and normal. So I take P and I define, for example, well, I would say, we were saying P minus P naught. Well, P minus P naught as a vector is good in the sense that it's orthogonal to the tangent space at every point. We know it, okay? It's the characterization of the tangent space to the sphere. But it is not normal, unitary. Nobody's telling me how much, in fact, nobody's telling me. Somebody's telling me how much is the norm of this. How much is the norm of this? R, by definition of the sphere, okay? So if I want to take a unitary normal, I need to take this vector divided by R, okay? Now this will be of length 1 and orthogonal to the tangent space. Of course, I could have taken minus this, okay? It would have been a generally good choice, also this one. For example, example 2. In your list of examples of regular surface, the simplest next thing is what? Graphs. Graphs of functions. So if S is something like the graph of a function f, as the little example we did at the beginning, whatever f is, are we able to produce an unit normal? Well, you can rely on the lemma, on the first lemma we proved, because we know that on each piece of a surface which is covered by one chart, you know how to define a unitary normal. That was the content of the lemma. But then graphs can be covered with one chart. So take the proof of the lemma, apply it to this, and that's it. And in fact, that's what you do. Now, x, what is x in this case? X of uv is uv f of uv, okay? And what was the lemma telling you? Construct nx. So nx was the vector field, the cross product of xu with xv normalized. Well, let's do it. This is 1, 0, partial derivative of f with respect to u. Cross product, wedge, 0, 1, fv, normalized. Okay, so divided by its norm to have it normal. Okay, so let's do it. Pick your favorite way to compute the wedge product. So this is the 1, 0, 1, 0 fu, 0, 1 fv. How much, which vector is this? This is fu. Sorry? Minus fu. Second? Okay, this is the vector product. Okay, so this is the vector, minus fu. Oh, in fact, since I hate to write two minuses, I change sign. Why not? I can pick n or minus n, it's the same. I mean, it's another unitary normal. So this is fu, fv minus 1 divided by its norm. What is the norm of this? This is square root of 1 plus fu squared plus fv squared. Okay, if you want to short it a little bit, this is, of course, the gradient square of f, for example, but I mean, as you want. Okay? So this is the vector nx. And now, if you really want to produce n, you have to just to write down nx composed x inverse. And that's it. Okay? Example 3, the most sophisticated class of regular surface we know up to now is the one given by regular values of functions, the inverse image of regular values of functions. So, what does it mean? S now it's f inverse of A, of course under the assumption that A is a regular value. But we know already what is the tangent space. We have computed as a little exercise. What is that at a given point P, what is the tangent space to S? It's the kernel of the differential of F. And when we discussed that, we observed that you can write it in this form. It's the set of vectors V in R3 such that the gradient, the scalar product between the gradient of F at P and V is equal to 0. This was an equivalent way to characterize the kernel of this map. Okay? So it's written here what is a unit normal. I mean, so this becomes the set of vectors which are orthogonal to the gradient. So the gradient is a normal, okay, by definition. Okay? So n equal grad f over the norm of grad f is a unit normal. Okay? Again, grad f cannot be 0, otherwise P was not, otherwise A was not a regular value. By definition of regular value, that's something where the differential is non-zero. Okay? The differential and the gradient are represented by the same matrix here. So, okay. Well, so now here it starts looking like an accident. We have defined the notion of an orientable surface, and everything we know is orientable. So conjecture, everything is orientable. For what you know up to now, this is a very logical conjecture. Okay, you will solve it. You will disprove this conjecture in an exercise, in the next homework, but you certainly know why it's not true. The typical example, the simplest example you can think is this. Take a rectangle. If you glue it in this way along a side, you get a cylinder. Is a cylinder an orientable surface? Yes. Yes, for example, it falls here. Okay? But you can also imagine pictorial, geometrically, there is no problem in going around the whole cylinder with a unit normal vector pointing in the same direction. Okay? But now you can play the other game. Glue the two sides of the rectangle in a way, so here before, to produce the cylinder, you had this point glued to the same point at the same distance from the long side to the other side. Now do the opposite. So take this point here and glue it to the opposite point, to the symmetric point. So the distance between this point and the long side here will be the same as the distance of the corresponding point to the other long side. Okay? Now, it's difficult to do it with a piece of paper because, I mean, with this type of paper, because, of course, it tends to break. But you can do it. Okay? And actually, this is the source of many famous pictures. Okay? Ants are there because general people don't like to speak about unitary normals. So the insect here is your unitary normal. Okay? This is a famous picture by Escher, who was a kind of mathematical fanatic, okay, of the end of the 19th century. Okay? Now, of course, the surface here is this net. Okay? And the way the ants are moving is telling you exactly that you cannot define a unitary normal. Okay? Because if you move along with the ants, so instead of the ants, put a little flag, which is really a more mathematical, sensible unitary normal. Okay? Move with the ants. Okay? When you have done a loop, you have come to the same point on the surface, but the ants is on the other side. Okay? They will not meet. They have to go around twice to meet. Well, good question. First, is it a regular surface? Otherwise, we are speaking about something else. This will be the first question in the exercise, okay? It is actually a very simple surface. You will see the analytic expression of this surface is very simple. And then the point is, what is more delicate is really, what are these ends showing you is just that the obvious choice doesn't work. But we are mathematicians, and say, why should be the obvious choice? Maybe there is another choice of n. Okay? As mathematicians, we are forced to give a proof that you cannot find a unitary normal vector field, not just that the simplest thing doesn't work. Okay? And this is slightly more delicate. Okay? But these objects exist. So not every surface is an orientable surface. Okay? So when we are going to study surfaces, we have to specify explicitly whether this will be orientable or not. On the other hand, we have the first lemma. The first lemma is telling us, on the piece of a surface which is covered by a chart, you can make a choice of n. So also on this monster here, which is called the Möbius strip, by the way, it has a famous name, okay? The Möbius strip, on a piece of this surface, which is parametrized by an x, there is n. So now, because now we are going on with the theory of surfaces, assuming that there exists n. And so you might say, well, but what kind of surfaces are we studying? So this will be the theory not of surfaces. This will be the theory of orientable surfaces. That's true, but every surface is orientable locally. Okay? So whatever we are going to say from now on will work globally on a surface if it's orientable, or locally on a surface if it's not orientable. But it will work. So whatever we are going to say, depending on local things, it's completely general. Okay? So we are not really restricting too much our study. Okay? Now, because now we really have to face the key problem of this course. The key problem of this course is, what does it mean that something is flat, and what does it mean that something has some curvature? Okay? This is kind of, once we understand this, we have done 75% of our course. Now, but let's follow intuition. So what is flat? Well, for example, the plane, whatever we are going to define, the plane should be flat. Okay? Otherwise, there's something really funny going on. And how which way we can characterize the plane. In terms of the normal vector or the tangent space, of course, knowing n and knowing the tangent space is the same thing in R3. Because if you give me the plane, I have n. If you give me n, I take the orthogonal complement, I have the tangent space. So philosophically, it's the same amount of information. It's more convenient to work with n because it's a single vector, while TPS is a plane in R3. So it's more difficult to handle. On the other side, I have just one function, okay, n. Now, how do you characterize a plane? We have seen it. N is constant. Is this a characterization of the plane? So basically, n is constant if and only if. We have proved if it's a plane, n is constant. The other way around, of course. Meaning, geometrically, the tangent space is always the same. If n is constant, the tangent space is always the same plane. Okay? So, first intuition, maybe curved or non-curved, flat or non-flat, depends on how much the tangent space changes. Because you would like to say, well, if I start doing something like this, I introduce some curvature, and in fact, n stops being a constant map. Okay? Well, we will be careful about this. But certainly, it's an intuition we have to follow at the beginning, okay? Meaning, you see, I'm trying to convince you that it's time that we study derivatives of n. So now, the key point is n and its derivatives, what kind of information we can extract out of them. So, and general warning that I will not do anymore. I take n from S to R3 a unitary normal vector field. That means either I'm taking an orientable surface or I'm taking a piece of a non-orientable surface. I assume that n exists. Okay? Now, in particular, n doesn't just go to the whole of R3. I know a bit something more because since n of p, the norm of n of p is equal to 1, n of p is a vector where? On the sphere. So in fact, that it's better to underline it. So n is really a map from S to the sphere of radius 1 and center the origin. Okay? And this is still a differentiable map. Remember, the definition was a differentiable map here, but this is still a differentiable map now between surfaces because it's the restriction of a differentiable map in R3. Okay? So now n is called, this map written in this form is called the Gauss map of S. Okay? But now it's a differentiable map between two surfaces, and we are very interested in knowing how much n changes. We know how to do it. Now, you should feel satisfied of having paid the price before. You just take, you know what it means to compute the differential of this map. Okay? And where does it go? So, where is the differential of the map defined? Well, at the point P, takes a tangent vector to the first surface at P, and where does it go? It goes to the tangent space to the image surface at the image point. Okay? So, this will go to T, n of P, S0, 1, S2, okay? On the other hand, what is the tangent space at a given point to the sphere? It's the orthogonal to the point itself. Now here there is not P naught, no? Because P naught is the origin. So it's really the point itself. But this object here is canonically isomorphic to what? To the orthogonal complement of this vector. obvious notations. Okay, this is the set of vectors orthogonal to n of p. But which are the vectors orthogonal to n of p? By definition of n is what? N is a vector orthogonal to the tangent space. So what is the orthogonal complement of n? The tangent space to the original surface. Remember, in all these things, what is important is that these isomorphisms are natural, canonical. Because, of course, these objects here are, of course, isomorphic. These are two-dimensional vector spaces. So they are all isomorphic to R2. Here, the key point is that these isomorphisms are canonical, natural. They do not depend on a choice of a basis. Okay? But then look what happened. The differential of the Gauss map, at the end of the story, takes a tangent vector to S at a given point and gives me back a tangent vector to S at the same point. Okay? This just is an accident of the sphere. It's this accident of the sphere which keeps on coming back. So it's an endomorphism of this vector space. Well, but then let's study which kind of properties does it have. Theorem, and this actually deserves the dignity of the word theorem. DNP is a symmetric endomorphism. Endomorphism means just it's an homomorphism of the vector space to itself. Okay, invertible. I mean, that's to a vector space to itself. And a symmetric endomorphism of TPS. Remember, what does it mean symmetric? I reminded you in the little exercise about the differential of the map. That means that if you take the NP of a vector V and you take the scalar product with another vector W, this is equal to V dNP W for every choice of V and W in the vector space that you are looking at. So for any V and W in TPS. Okay? So this in formula. That's what you need. Well, let's prove it, and actually, as usual, in the proof we will find interesting formulae. I need a bit more of space here. Proof. Well, if you want to check that something is a symmetric endomorphism on a vector space, it's enough to check it on a basis. Okay? If you have a basis, you can check it on the basis. If it works, that's it. Okay? So it is enough to check it on a basis. The problem is, which basis? Do we have a basis? Well, yes. We pick a point P, and we pick, as usual, a local chart around P. Once you have done this, you have a basis, XU, XV. Okay. The problem is, of course, if I want to check a formula like this, so you see now V and W will be XV, XU, XV. So it's clear that the whole point of the proof is, are you able to tell me something about this? I mean, can you compute it in some way? Of course, and the same for XV. Well, let's go back to the definition. What is a differential of the map applied to a vector? As usual, what do I have to do? I have to take a curve passing through alpha, passing through the point P at time 0, with velocity, the vector that I'm looking at. Okay? So alpha of t now will be a curve x of u of t, v of t. So now Here, this is one of the points where you have to be careful about this ambiguity I was telling you at the beginning, because now I'm writing. So this is alpha is a curve on S, okay? But actually, I'm automatically taking the inverse image of the curve on the domain of the chart. Okay? Automatically. We have done it already 3 or 4 times, and we are old enough to do it by default. Okay? So, and the only thing I'm asking is alpha of 0 is equal to P at the moment. So how much is dNP? So let me write it in general. And now, depending on the choice of alpha, I will impose that this is equal to this or this is equal to the other one that I care. Okay? How much is this? Well, first, I can use chain rule to express alpha prime at 0, because see, alpha is a composition of 2 things. No? It's a curve in the plane composed with x. So this is, first I can do this. dNP of what? Of u prime, so the derivative of u with respect to t times the derivative of x with respect to u. Okay, chain rule. Now, this is equal to, by linearity, the differential is always a linear map, so this sum splits as the sum of the images, and these are scalar, are numbers, so they go out. So this is u prime 0 dNP xu plus v prime 0 dNP xv. Now, how do I get xu and xv? Well, xu is by definition, what is the partial derivative in one direction? If this is u and this is v, and you have a function which depends on u and v, what is the partial derivative in the direction u at a given point? Well, by definition means you restrict your function to the line passing through this point parallel to the direction where you are taking the partial derivative, and you take the derivative in the usual sense, in the old sense of a function of one variable. Okay? Well, but that means that this object here is automatically the partial derivative of the map n. Actually, here probably should have been more nx in the language, but I'm using that mistake I was telling you, n derivative with respect to u, plus v prime 0, n derivative with respect to v. Okay? It's okay. Well, convince yourself. This is automatic by the definition of the differential and by the definition of the partial derivative in one direction. Okay? So this object here becomes automatically the partial derivative of the map in the direction that you are using here. Okay? Now, so this is general picture. Now, what is the symmetric condition asking us? Well, so written in this form, now that we know this here, this is asking n of u times xv. Is it equal? So equal with question mark, because this is the content of the theorem. Is it equal to xu and v? Okay, do you agree that now this is the problem? Now, how do I get to this equation? Well, I take the only thing I know. Xu, xv is a basis of the tangent space, and n is a normal vector. What does it mean? It means that n scalar product xu is equal to 0 at every point, because this is tangent and this is normal. And of course, also, maybe yeah, it's better to write it in another line, n xv is equal to 0 for the same reason. One is tangent and one is normal. Then how do you get here? You see, well, let's do it. It's simpler to do it than to justify it. I mean, I take the derivative of this equation with respect to the missing coordinate here, v. So let's take d in dv of this equation. Of course, if I differentiate 0, I get 0. And take d in du of this. Well, actually, here, strictly speaking, I should put the partial derivatives, okay? How much is this? Well, the first one, as usual, scalar product is differentiated as a standard product. So derivative of the first, nv xu plus n xuv, second derivatives, okay, with obvious notation. And the other one becomes what? Nu xv plus n, well, I should say xvu, but then standard calculus tells me that the order is irrelevant. Xvu is equal to xuv. Okay? And so I'm done. Why am I done? Because both are 0. So take this up. So that means nv xu is equal to minus this. But nu xv is equal to minus the same thing. So in particular, they are the same. Okay? They are the same, and in the future, I might be interested in knowing that they are not just the same, but they are actually, so this proves that this is not a question mark, but also that they are both equal to minus n xuv, which could be useful. It's an extra thing that was not required in the statement of the theorem, but why not? We learned it, we take it. Okay? Right, so what does a mathematician do when you have when he or she has a symmetric endomorphism of a vector space? It looks to the associated quadratic form. It's always the same thing, so let's do it also in this case. Even though the knowledge of the endomorphism and the knowledge of the associated quadratic form is the same, okay? So you have the same amount of information. It's just a question of what you prefer. So since Gauss preferred the quadratic form, we shut up and we study the quadratic form, okay? So in this particular case, you give this strange symbol. It's a second. It's a Latin second with a P, okay? So this is the quadratic form. What does it mean, a quadratic form? It has to take two vectors in the vector space. So it goes from the Cartesian product of the tangent space to the surface to itself, and gives me a real number. And how you do it? Well, you take two vectors, two tangent vectors, v and w, and actually here there is a usual source of mistakes also inside my lectures. So part of the exercise is to check that I sometimes don't forget this minus sign. Okay, you put minus dnp v w. Okay? This is completely general. How to associate a quadratic form to an endomorphism of a vector space. A symmetric endomorphism of vector space. Okay? Now this is called the second fundamental form. Second fundamental form of S at P. And basically it will be the topic of our study up to the end of the course. But now, the first question when you define the second fundamental form is where is the first, okay? So the first, we actually used it without even giving it a name, but why not? I mean, let's give it a name. So the first fundamental form is, again, it's another quadratic form. So it takes, again, two tangent vectors and gives a real number, takes VW, and just gives me the scalar product. We never felt it, the necessity of giving it another name different from scalar product, but okay, so and this is called the first fundamental form. First fundamental form of S at P is just the scalar product restricted to the tangent space, the scalar product of R3 restricted to the tangent space, to the surface. Okay. And now, here, let's start with a list of definitions, because since the differential of the Gauss map is a symmetric endomorphism, in particular, it is diagonalizable. Okay? In this case, you don't even need what we... So the NP symmetric implies diagonalizable. Now, diagonalizable, of course, not diagonal. I mean, you don't even diagonalizable. Okay? But diagonalizable. So that means that there are two numbers which are more interesting than other numbers, and two vectors which are more interesting than the other vectors. The two numbers are the eigenvalues. So we define K1 of P and K2 of P are the eigenvalues of minus dnp. I mean, of course, if dn is symmetric, also minus dn is symmetric. Okay, this is just a sign convention. And how do I decide? So, of course, this is diagonalizable. So it has two eigenvalues counted with multiplicity. I mean, in principle, they could be the same. So how do I choose which one I call K1 and which one I call K2? So the assumption is that K1 of P is less than or equal, is the smaller one. If the smaller one, whenever it makes sense. Because if they are the same, but on the other hand, if they are the same, who cares which one you call K1 and K2? They are the same, okay? So whenever they are different, one is smaller, and the smaller gets the one, okay? Becomes the first. In any case, so this is the notation, but we call them, so these are called principal curvatures of S at P. What do you do with the eigenvalues of a symmetric operator? Many things. But in particular, so which are kind of the characteristic numbers of a symmetric operator in dimension 2, the determinant and the trace. These are the only two things that you can do, the only two symmetric functions of the eigenvalues, okay? So it's likely, they are likely to be important. So capital K at P is the product times the product of the two eigenvalues, which of course, if you want, is the determinant of the matrix. Okay. This is called Gauss curvature, or Gaussian curvature is the same. Gauss, from time to time, Gaussian curvature. Of course, of S at P, I don't repeat it. 5, the trace. The trace is what? And here, this is another source of usual mistakes, because it's the average or it's the sum. From time to time, you forget the half, but in the beginning, you put it. And this is called the mean curvature, of course, of S at P. And that's it about numbers, but now about vectors. We have to give names to some special directions. So the directions, so here you have to be, I mean, it's kind of long to say, but the directions associated to the eigenvectors. Because you see, a single eigenvector is nothing. I mean, twice an eigenvector is an, which eigenvector do I choose? There is no choice of a better one. The only interesting thing is the direction of the eigenvector. Okay? So that's why I don't give a name to a one eigenvector. I give the name to the span of the, so to the eigenspace in some sense. Okay? So the directions associated to eigenvectors, but now I have to order, again I order them, V1, V2 associated to K1, K2. So K1 will be associated to V1, K2 will be associated to V2. These are called principal curvature, principal directions. Of course, remember, everything depends on the point. So at a given point, you have two numbers, the product, the mean, these directions. Okay, but if you change point, you have change numbers. Okay, and now final thing, final name, a curve alpha from some interval to S is called a line of curvature if its tangent, its velocity, its tangent vector, so this is in particular a tangent vector to the surface S at alpha of t. So of course there will be a special class of curves, those for which the tangent vector at every point is a principal direction. Okay? So a line of curvature, if alpha is a principal direction, Now let me be of S at alpha of t, no, at the corresponding point, of course, for any t. Okay? You have a question? No, it's okay. I mean, you are encouraged. This is a bunch of names, okay, nothing to be, the key point, the important, the heart of the point here is that the differential of the Gauss map is a symmetric endomorphism. That's the mathematical point. Then everything else is just giving names to the associated objects, okay? Examples. Let's compute some of these things in the examples we have, okay? For example 0, the plane. Sorry, may I erase? Example. So let's start with 0. S is equal to a plane. Well, what is the Gauss map? N. Let me write it here. N from S to S1, meaning, sorry, S2, 0, 1. Okay, we decided that if I don't write anything, it's with center the origin and radius 1. So we have already said it. I mean, this is a constant map, which takes at every point, associates the normal vector to the plane. Very good. So how much is dn? How many votes for 0? You don't reach majority. How do you do it? Think of what is this. You should take a tangent vector to the plane, whatever. Take a curve in your mind alpha, such that alpha of 0 is p and alpha prime of 0 is v. Take n composed alpha, no? In general, the function composed alpha, and take the derivative at time 0. Whatever alpha is, n composed alpha is always the same vector, because n is constant over the whole plane, so whatever alpha is, n composed alpha is a constant vector. So the derivative at time 0 will be 0. Okay, I don't have to make any computation. But, so of course 0 is a symmetric endomorphism. What are the eigenvalues? So principal curvatures of the plane, both 0. Gauss curvature, 0. Mean curvature, 0. Which are the principal directions? There are infinitely many in this case. You see, because of course, in general, you give the definition thinking, well, I have one eigenvalue, I associate one eigenvector, and that's it. But of course, if the two eigenvalues are the same, the eigenspace must be the whole tangent space. But that means that every vector is an eigenvector. Okay? So every direction is a principal direction. So which are the lines of curvature? Any line, any curve. Any curve on a plane is a line of curvature. Okay? Because there are no restriction on the tangent space, on the velocity. Okay? Well, this is of course example 0 for a good reason. Okay? Example 1 is always the sphere. So now let's take the sphere with something, okay? P naught of radius r, okay? We have written before, 1 hour ago, what is the normal, one choice. Now remember, and actually this is important and interesting, n is not uniquely defined. So when I compute these numbers, or these directions or whatever, I have to tell you which choice of n I'm making. It's not something that comes with the surface by itself. I know, the only thing I know, and it's important, is that actually I give you my choice of n, and you could take another choice, but actually there is not too much freedom among us. So you either pick mine, or you pick minus mine. There are always only two possibilities. Okay? But actually, this minus can have an effect, may have an effect on these numbers. So, in fact, it has an effect on these numbers. So I have to tell you, not just S, but which n. I mean, this was irrelevant here, because anyway, it would have been a constant. Pick mine or minus mine, it was, in both cases, a constant vector. So whatever we said in the example 0 was okay. Now it's important. So n from S to P naught R. I have to tell you which normal vector I choose. I wrote one possibility before, and I take that one. Okay? Now, with this choice, how much is dn? Well, now you should start being able to do it. Take alpha, with alpha of 0 is equal to p, with alpha prime is equal to v. Take n composed alpha, which just means substitute at p, you put alpha of t, and take the derivative at time 0. Well, the derivative of this object at time 0 is, of course, alpha prime of 0 divided by r. Alpha prime of 0 is v, so this object is just 1 over r v. Okay? Now, please, you have to become, I mean, I hope I've made enough examples, okay, to make you quick. So what is the second fundamental form? at a given point, well, it's the quadratic form which takes two vectors v and w and gives you, I should write minus d and p. So in fact, maybe I want to write minus 1 over r vw. It's not a nice r, okay? In any case, so this is the second fundamental form. Which are the eigenvalues of minus d and p? Remember, K1, the principal curvature are the eigenvalues of minus d and p. Well, it's written here that the differential of the Gauss map is a multiple of the identity. And the factor is 1 over r. So the eigenvalues are 1 over r. Both. I mean, there is only one eigenvalue with multiplicity 2. Okay, so K1. Of course, this is true for d and p. I'm looking at minus d and p. So K1 of p is actually equal K2 of p is actually minus 1 over r for any p. So what's going on? Now, this time, the principal curvature are not 0, but still, they are constants. They don't depend on p. Okay? In any case, these are the numbers. So, of course, what is the Gauss curvature? Is the product. So, it's 1 over r squared. What is the mean? The mean of two, it's the same. It doesn't change. And what else? And which are the principal directions? Sorry? You can take any vector. Any vector is an eigenvector. So again, we fall in the same situation as the plane. Any direction, any tangent direction is a principal direction, and so any curve is a line of curvature. So actually, this is a good point where to check. What if some of you prefer minus mine Gauss map? It would have been perfectly logical and, okay, there is not a right choice. There are just two choices. So if we take minus this, here I get a minus, so the differential becomes minus. So K1, K2 change sign. They become positive 1 over r. So the mean curvature changes sign. The Gauss curvature doesn't care. Okay? Now think, is this a special situation of the sphere? It's a totally general situation. So the choice of the orientation, so we introduce another word, obvious, okay, so which means the choice of n, the choice of the orientation has the effect of switching sign to H, K1 and K2, and it's irrelevant for the Gauss curvature, okay? Okay, next example is a bit long, so we stop here.